Good afternoon. It's my pleasure to be here in Iceland once again. Reykjavik is a very beautiful city and I really enjoy coming back to it. And Reykjavik, of course, is also in an area that is directly affected by the larger Gulf Stream system, the extension of the Gulf Stream, the North Atlantic Current. So I want to discuss whether the Gulf Stream system is slowing, and the reason why we are concerned about this is, of course, that we are in the midst of a rapid global warming. This diagram shows the NASA data up including last month and shows a 12-month running average. And you see this very clear rise in temperatures. And if you look at the pattern of that temperature change, if you look at the linear trends from 1901 to 2013, you can see that practically every part of the planet has warmed, but there is one big exception, and that is exactly the area to the south of Iceland, which has shown a cooling. Luckily, maybe for you, where it's already very cold, it's not above the land in Iceland. The land temperatures have also warmed in Iceland, but not far away to the south of it, we have this cold patch in the North Atlantic. Now, that tells us something because this region is exactly in the area where this ocean circulation in the Atlantic is dumping a lot of heat. It brings warm water up to that region, gives off the heat to the atmosphere. That cold water then becomes dense enough to sink down and return at depth to the South Atlantic and join this overall large-scale circulation of the global ocean.
Something extraordinary and disturbing, that is. You recall what you said in New Delhi about how polar melting might disrupt the North Atlantic current?
Yes.
Well, I think it's happening.
What do you mean?
So that is the Hollywood take on this. And that is exactly the topic that I want to discuss today. Is it happening? First of all, here is a schematic diagram showing you what this global ocean circulation looks like. And of course, this is still a highly simplified diagram, although it might look complex to you. In reality, of course, the ocean is highly turbulent and has lots of eddies and meanders and small-scale structures. But this is still a valid scheme of the overall transport of water masses around the globe. And the North Atlantic is special in this respect, in that unlike the North Pacific, there is deep water forming there. That's what the orange dots indicate, is its region where water is sinking and then returns as so-called deep boundary currents towards the south. And it's clear that if warm water comes towards you and cold water goes away from you, it works like a central heating system, delivering a lot of heat. And that is largely responsible for the very mild, comparatively mild temperatures in the North Atlantic region compared to other places on the same latitude. Now, we don't have direct measurements going back many decades or even a century to tell us what this ocean circulation has been doing in the past, so people have turned to indirect ways of deducing that. And one of the early studies was from my colleagues Dima and Lohmann from Bremen, who looked at sea surface temperature evolution since the year 1870 and identified particular patterns. The first pattern was, of course, global warming, but the second pattern, which is called the EOF number 2 here in the scientific jargon, that stands for empirical orthogonal functions. That's how we analyze space-time patterns. And that pattern has a kind of big blob in the subpolar Atlantic. It has the opposite phase in the South Atlantic, and it also shows a bit of a dipole between the subpolar Atlantic and the Gulf of Maine area of the east coast of the United States. And I'll return to this particular feature later on. That's why I'm pointing it out here. Now, the time evolution, the time curve that belongs to that pattern is shown at the bottom there. And the fact that this shows a downward trend translates into a cooling in that red blob there in the subpolar Atlantic. So this is completely consistent with the linear trend that you showed you in the earlier diagram. And these authors noticed that there was an anti-correlation between North Atlantic and South Atlantic in this respect, so they calculated a correlated pattern of change, and that's what you see on the top right there. It's a coupled correlation of the North Atlantic with the South Atlantic, and this anti-phase coupling between North and South Atlantic is very characteristic for changes in the heat transport by the ocean. Because if the ocean transports more heat northward, the north gets warm and the south gets cold, and vice versa. So this anti-correlation is a telltale pattern. And here again, in this coupled correlation pattern, you also see this dipole between the Northwest American shelf there and the subpolar gyre region to the south of Greenland and Iceland. And they concluded that the global conveyor, which is another term for this overturning circulation, has been weakening since the late 1930s. That's a very clear statement, so that already almost answers the question posed in the title of my talk: is the system slowing down? These authors said yes, and I could finish the talk here, and then we could have an early coffee break, which would be quite nice in many ways. But there is more to say about this, and in case you're interested, then stay here and don't have coffee yet. If we look at what happened last year, for example, 2015, this is a diagram published by NOAA. This area in the subpolar North Atlantic was at its coldest on record since the year 1880. That is really amazing, given that this was the warmest year on record globally. So hottest year globally on record, coldest in the subpolar North Atlantic. That is quite striking. Here is what models are saying. This is the kind of highest resolution, latest, best climate model that I have seen. It has a stunningly good resolution in the ocean. That's 10 by 10 kilometers roughly, very fine resolution. And in this by the Geophysical Fluid Dynamics Laboratory in Princeton. And they subjected this climate model to a standard idealized global warming scenario by increasing carbon dioxide levels in the atmosphere of that model 1% each year. That translates into a CO2 doubling after 70 years. That's faster than the kind of future projections that are more detailed and more realistic about emission scenarios. But it's a standard run that climate modelers like to run because it can be compared directly with a whole suite of historical model simulations that have been done. And here you see the response to that CO2 increase is, again, general warming, those green colors between 1 and 2 degrees warming there, a cooling in the subpolar Atlantic to the south of Greenland, and this warming on the Northwest American shelf there. That's excessive warming in this region. And the authors of that paper, they conclude that this particular pattern here is a consequence of a change in the overturning circulation, which we call AMOC, and they find that by comparing different model runs, and they find that the strength of that pattern there is proportional to how much the Atlantic overturning circulation has weakened in that particular model. So it's a clear indicator that this is indeed to a weakening of the Atlantic circulation. So that is something that climate models generally do predict, that this will be a response to global warming. Now, we published this paper last year at just exactly 1 year ago. It's a cover story of the journal Nature Climate Change at the time, where we looked at this pattern specifically. And here in this diagram, you see a comparison of the region that models predict where you get a cooling when you slow down that circulation. This is the average of a whole suite of models that was published quite a few years ago. And in blue, you see the observed cooling pattern. So the white contour is the model prediction for a slowdown of the Atlantic circulation. Blue is the observed cooling. And you see there's a pretty large overlap between the modeled response to a slowdown of the circulation and what we actually find there. The Labrador Sea on the left here differs between the models and the observations, but that is not surprising because in those models there was a much stronger weakening of the circulation than we observed so far, and in those models the deep water formation, the convection happening in the Labrador Sea actually shut down. That is not something that has happened yet. That may well still happen in the future, but that I think explains that difference here. But basically what we did, we said we take the pattern from the models, the expected cooling from the models, and use this as a telltale pattern to derive how much the circulation has changed by taking the temperature in that region minus the average temperature of the northern hemisphere. So we subtracted the whole northern hemisphere temperature evolution out of that in order to subtract out the overall global warming signal, which would otherwise distort what we get here. And so we have to take the difference. And whether this actually works, whether it gives reasonable results, we can test in a climate model where we have the full information, namely where we know what the actual circulation is doing. And this diagram shows from the climate model the strength of the overturning circulation in red in a standard global warming scenario. And in blue, it shows that index derived from the sea surface temperatures in the subpolar North Atlantic minus the rest of the northern hemisphere. And you can see that there is indeed a pretty good correspondence between those two curves, so that our kind of method of deriving the ocean circulation based on a telltale sea surface temperature pattern has passed this test in the model world. And that's why we decided it is probably useful to apply this to real data. And together with my colleague Michael Mann and other colleagues, we used proxy data that go back about a millennium here. And these were pre-existing proxy data that had been published by Mann and colleagues in 2009 in Science. And they show predictive skill, these proxies, for temperatures in the subpolar Atlantic. And that's why we felt it is justified to calculate this index for an Atlantic overturning circulation based on the sea surface temperature patterns that are found in these proxy data for the last 1100 years. And the curve that we got looks like this, which indicates that in the 20th century, at the end here, the overturning circulation indeed goes down. It weakens. That is basically seen in that cooling in the subpolar Atlantic. But in the 1,000 years before that, nothing like that has ever happened before. So we concluded here that the weakening and the subpolar cooling that we see in the 20th century is unique in at least a millennium. That didn't really surprise us that much because we, of course, expect this to be a response to global warming, and we know that in the last millennium there never has been such a global warming as in the 20th century. And the models predict this kind of weakening of the overturning circulation in response to global warming. But this confirmed that indeed this 20th century weakening is quite special and outside the kind of natural variations that you expect in the Atlantic overturning circulation. The darker blue thin line at the end, by the way, is the same thing derived from the direct temperature measurements with thermometers that kick in the late 19th century. So for the last 100 years or so, we have those direct measurements, and they agree pretty well with what the proxy data are telling us.
What about the North Atlantic current?
What about it?
The current depends upon a delicate balance of salt and fresh water.
We all know that.
Yes, but no one has taken into account how much fresh water has been dumped into the ocean because of melting polar ice. I think we've hit a critical desalinization point.
So there were two things mentioned there. Nobody has taken into account of how much meltwater comes off Greenland. And here you see the satellite data showing the mass loss of Greenland. And it is indeed true that most climate models do not account for the meltwater runoff from Greenland and the mass loss of Greenland, because these climate models traditionally have been ocean atmosphere models. They have sea ice, but they don't actually have a continental ice sheet model embedded in them that would provide them this meltwater input from the Greenland ice sheet. And in that sense, there is a reason to think that the climate models would underestimate that weakening of the overturning circulation in the North Atlantic. Only recently, climate modelers have started to embed ice sheet models in their global climate models. And there were only a few exceptions with lower resolution models applied to paleoclimate research, which did actually have coupled in ice sheet models. And there has been a recent estimate of the amount of mass loss from Greenland. And in our paper, we discuss this estimate, and the cumulative estimate is shown here. And just for the period from 1900 to 1970, that amounts to an addition of fresh water of 8,000 cubic kilometers. And for comparison, probably the largest oceanographic anomaly that had been observed in the 20th century was a so-called Great Salinity Anomaly in the North Atlantic, in that subpolar Atlantic in the 1970s. And that was equivalent to a freshwater anomaly of 2,000 cubic kilometers. So just comparing those numbers already tells you that the mass loss from Greenland is quite a large number and is bound to play some role in the observed freshening in this area. That is indeed also an observational fact that in the high latitude Atlantic, salinity is going down, whereas in the subtropical Atlantic it is increasing. So Greenland mass loss probably played a role. The second point that is made in this little clip from the film is that there's a critical desalination point, and that indeed is also true. We call it a bifurcation, and this diagram is a stability diagram for the Atlantic Ocean circulation, and it's been known since the 1960s, since the work of the famous American oceanographer Henry Stommel, that the North Atlantic overturning circulation has such a critical tipping point beyond which it will basically collapse because there is no more stable, steady state for this circulation available. In this diagram, the slightly darker highlighted region there, that is the part where there are two stable equilibria, this upper branch and the lower branch. To the left of it, you have only one stable equilibrium with the overturning circulation in the Atlantic. To the right, you also have only one, namely without overturning circulation in the Atlantic. And we don't know exactly where in this stability diagram we are today with the circulation, but there are indications that we are in that middle part where there are two stable equilibria, which is not too far away from that critical point where the circulation could collapse. The problem is that indeed we can discuss that there is some risk that we can possibly cross this critical point, but we can't really predict that because it's a highly nonlinear phenomenon that is sensitively dependent on exactly the balance of salinity and temperature in the Atlantic, etc. So I don't think anyone has ever dared to make a concrete prediction of how far off that critical point we might be. Oops, another error message. What do we do now? Let's just do like the governments and click ignore. So I want to come back to this high-resolution model simulation from the colleagues at Princeton. They found that this warming on the Northwest American shelf in response to a weakening of the Atlantic overturning circulation, it's related to the Gulf Stream shifting northward when this overturning weakens, and thereby the warm Gulf Stream waters entering the shallow shelf areas there into the Gulf of Maine is the region that you see there, where you see those red bits. And in that region, warm Atlantic waters from the Gulf Stream replace the previously present cold waters from the Labrador slope that used to be there. And so that's what the model predicts in response to global warming and weakening of the overturning circulation. Now, as it happens, exactly from that region there, this northeast channel and the Gulf of Maine, we have proxy data or rather some US colleagues have those proxy data, and they published those already a few years back in proceedings of the National Academy. And these are based on corals, and these colleagues have analyzed the isotope composition of the corals, and especially looking for nitrogen-15 isotope, which depends on the kind of water mass that the corals live in. And they find this strong decline, this curve that you see there in the 20th century. And what this indicates to them is a replacement of cold Labrador waters with warmer Gulf Stream waters. Is exactly what this model simulation predicted for a weakening of the overturning circulation. So you could argue that this downward curve there in the 20th century from the corals is indicative of a weakening of the Atlantic overturning circulation. And the interesting part of this is also that while they don't have a continuous coral record before 1930, they have found some bits of older corals that they could analyze and date. And these are the 4 points there, and they are all on the higher end. So the colleagues conclude that this situation that we have since the 1970s there with the very low values of this nitrogen-15 is unique in the context of the last approximately 1800 years. That's of course not based on a lot of data, so it's a tentative thing, but it is in agreement with what we found based on our sea surface temperature proxy data, which suggested that this weakening in the 20th century is actually unique in the last millennium. Now we took this curve there, the coral curve from 1930, and show it in our paper together with our Atlantic overturning index from sea surface temperatures. So the coral data are in green, and the blue and dark red curves are from 2 different surface temperature data sets, from instrumental data in this case, the index of the Atlantic overturning. And you see there's a pretty good agreement that the circulation has weakened until around about 1980, 1990, and after that it has recovered again somewhat into the early 2000s, and then around about 2005 or so it turns downward again. Now that, oh, sorry, I forgot something there. That is actually in good agreement with the measurements. We have only very short series of direct regular measurements of the Atlantic overturning circulation since 2004. It's called the rapid array, and that just started in the beginning where we see this downward turning, and has measured until today a trend of a weakening by about 3 Sverdrups, which is compared to the mean circulation of about 15 Sverdrups, and is in agreement with what our index suggests there. So this last bit is in good agreement with the direct observations. And various other aspects of this time evolution are in agreement with other attempts with the help of models, etc., to reconstruct what the Atlantic overturning circulation has actually done in recent decades. Now, to finish off, I want to look at some of, at least very briefly, some of the consequences that such a weakening of the overturning could have. One of the consequences is on sea level. Climate models predict that if the Atlantic meridional overturning circulation slows down, then the sea level on the US coast will go up, whereas basically on the left of the Gulf Stream it goes up, on the right-hand side it goes down, as you can see in this diagram. So that is a pattern that would be superimposed on the total global sea level rise here, and it would lead to a disproportionate rise on the US coast, maybe 20, 30 centimeters extra there on top of the global average rise for people living there in that region. Another consequence, of course, is the effect on the weather, and we are really only beginning to understand this with reasonably high-resolution models. Here is a publication by British colleagues that shows the effect of a decline of the overturning circulation on the storm tracks, and they predict with their model that it would significantly strengthen the storm track hitting into Britain and across the North Sea into Holland and Germany. There are potential other effects also on the weather on the United States East Coast, for example, but I don't have time to really discuss all the potential impacts. It's not going to be a new ice age. It's nothing like the day after tomorrow. That much I can reassure you absolutely. That film, of course, took its liberties with the laws of physics in many ways. But nevertheless, I think that such a fundamental major change in one of the great ocean circulation systems of our planet will have serious consequences on many levels. Now, to conclude, I mentioned that we have a lack of direct current observations going far back in time, so we need to use indirect measures, and we use the sea surface temperature pattern, a telltale fingerprint of the slowdown of the circulation, to conclude that there is evidence for an actual slowdown during the 20th century that is also unprecedented in the last millennium, and that this slowdown probably will affect climate and weather as well as sea level in ways we have not fully understood yet, but more and more people are starting to work on this now. And there is a risk of irreversible change, even though we cannot quantify it very well how close such a tipping point is, but it is another reason to apply the precautionary approach here and to implement the Paris Agreement to minimize this risk.
Should stick to science and leave policy to us.
Well, we tried that approach. You didn't want to hear about the science when it could have made a difference.
Thanks. But this is still a valid scheme of the overall transport of water masses around the globe. And the North Atlantic is special in this respect, in that unlike the North Pacific, there is deep water forming there. That's what the orange dots indicate, is its region where water is sinking and then returns as so-called deep boundary currents towards the south. And it's clear that if warm water comes towards you and cold water goes away from you, it works like a central heating system, delivering a lot of heat, and that is largely responsible for the very mild, comparatively mild temperatures in the North Atlantic region compared to other places on the same latitude. Now, we don't have direct measurements going. Good afternoon. It's my pleasure to be here in Iceland once again. Reykjavik is a very beautiful city, and I really enjoy coming back to it. And Reykjavik, of course, is also in an area that is directly affected by the larger Gulf Stream system, the extension of the Gulf Stream, the North Atlantic Current. So I want to discuss whether the Gulf Stream system is slowing, and the reason why we are concerned about this is, of course, that we are in the midst of a rapid global warming. This diagram shows the NASA data up including last month and shows a 12-month running average. And you see this very clear rise in temperatures. And if you look at the pattern of that temperature change, if you look at the linear trends from 1901 to 2013, you can see that practically every part of the planet has warmed, but there is one big exception, and that is exactly the area to the south of Iceland, which has shown a cooling. Luckily, maybe for you, where it's already very cold, it's not above the land in Iceland. The land temperatures have also warmed in Iceland, but not far away to the south of it, we have this cold patch in the North Atlantic. Now, that tells us something, because this region is exactly in the area where this ocean circulation in the Atlantic is dumping a lot of heat. It brings warm water up to that region, gives off the heat to the atmosphere. That cold water then becomes dense enough to sink down and return at depth to the South Atlantic and join this overall large scale back many decades or even a century to tell us what this ocean circulation has been doing in the past. So people have turned to indirect ways of deducing that. And one of the early studies was from my colleagues Dima and Lohmann from Bremen, who looked at sea surface temperature evolution since the year 1870 and identified particular patterns. The first pattern was, of course, global warming, but the second pattern, which is called the EOF number 2 here in the scientific jargon, that stands for empirical orthogonal functions. That's how we analyze space-time patterns. And that pattern has a kind of big blob in the subpolar Atlantic. It has the opposite phase in the South Atlantic, and it also shows a bit of a dipole between the subpolar Atlantic and the Gulf of Maine area of the east coast of the United States, circulation of the global ocean.
Something extraordinary and disturbing, that is. You recall what you said in New Delhi about how polar melting might disrupt the North Atlantic current?
Yes.
Well, I think it's happening.
What do you mean?
So that is the Hollywood take on this. And that is exactly the topic that I want to discuss today. Is it happening? First of all, here is a schematic diagram showing you what this global ocean circulation looks like. And of course, this is still a highly simplified diagram, although it might look complex to you. In reality, of course, the ocean is highly turbulent and has lots of eddies and meanders and small-scale structures.